record. Welcome everyone. I'm Xiang Chen. Today I'm going to present my work on the feasibility study for temperature fluctuation diagnosis based on soft X-ray imaging. Here's the outline of this presentation. As we all know, transport significantly limits fusion gain, and turbulence driven by the microinstabilities is believed to account for the large amount of transport rather than neoclassical process. Experimental measurements of turbulence fluctuations are very important for understanding transport properties directly from the experimental viewpoint, and also for that they are needed to validate gyrokinetic models so that we can better predict transport properties in new physical regime and new device. However, we are lack of experimental data of these kind of measurements, especially temperature fluctuations. Here shows a table of fluctuation diagnostics available today. From this table, we can see that the development of temperature fluctuation diagnostics run behind the density fluctuations, while they are equally important. Moreover, high K temperature fluctuation diagnostics is not available yet, while it is very important for us to understand the electron transport. That's why we want to develop temperature fluctuation diagnostics. And 3 techniques are considered for a new temperature fluctuation diagnostic: soft X-ray imaging, Thomson scattering, and CECE. In general, the achieved spatial and temporal resolution of soft X-ray imaging outperforms the other 2, so we decided soft X-ray as our first consideration. Here is a little background about soft X-ray. The key takeaway is the electron temperature can be measured with soft X-ray imaging by measuring the radiation power against the soft X-ray image energy. However, line integration is a problem. The solution to local measurements is computed tomography. The principle is we measure the line integrated emissivity data at different angles and different lines of sight and reconstruct the local emissivity with a tomographic algorithm. There are many different tomographical algorithms. One of the most popular and simplest algorithm is filtered back projection. For parallel projection, the reconstruction can be done with this formula directly if we have sufficient data at different viewing angles and different chords. Soft X-ray tomography has been applied in fusion research for decades, but hasn't been used to measure microturbulence. Previous applications are mainly related to MHD phenomena, which is not very demanding in spatial and temporal resolution. But for turbulence fluctuations, the requirements are much higher, while we are still subject to the same constraints. Very few ports accessible for camera installation and limited number of viewing chords. To overcome the constraints and meet the requirements for temperature fluctuation measurements, we propose a new algorithm called pseudo-local tomography, which is basically filtered back projection, but we accommodate more viewing chords around the region of interest to enhance the spatial resolution there. We implement filtered back projection for the global and local chords separately. This algorithm is valid because the global profile and the local fluctuations are separated on the wave number scale like this, so we can do the reconstructions separately. The key issue we are trying to address is how many viewing angles and viewing chords do we need to at least for a good reconstruction of the electron temperature fluctuations, and are the numbers reasonable in practice? So we came up with a model to test if the algorithm works. Given the measurements of line integrated soft X-ray emissivity, so we reconstruct the temperature fluctuations in the region of interest with the proposed algorithm. So we are trying to find out the minimum set of number of viewing angles and viewing chords at viewing chords subject to a good reconstruction of temperature fluctuation, and see if we can do it in practice. So we made a lot of assumptions in the model so that we can keep focus on the algorithm itself. Some of them are very ideal and have big impact on the reconstruction, but their effects will not be covered here, but studied in the future. So here's a flowchart of this model. First, we generate the synthetic data. We start from the electron temperature and density, including the fluctuations. Then we calculate the soft X-ray emissivity according to this formula. And last, we calculate the line integrated emissivity. Next, we use pseudo-local tomography to reconstruct the local emissivity from the brightness. Last, we do curve fitting to invert the electron temperature, and then compare the reconstructed results with the synthetic ones. This is assumed profiles of temperature, electron temperatures, and density and emissivity. And this is how the electron temperature fluctuation spectrum look like. This is taken from one of the gyrokinetic simulations. And this is how we generate the fluctuations. I'm not going into the details here. Just to show the generated fluctuations. These are temperature, density, and emissivity. So now let me introduce some of the key parameters in your model, the parameters for the fluctuations. So the radial wave number and the frequency are important because they will be used to compare with the reconstructions. And diagnostic parameters, so n theta is number of viewing angles, and global number of global chords, the red one here, and local is local chords, the blue chord here, and ms is the number of measuring points, the black dots here, and sampling rates. So these are the parameters we are trying to optimize. And in the following study, we change one parameter and fix others to study their effect independently. First, let's look at the reconstructed temperature fluctuations at the measuring points compared to the synthetic data. They appear to be quite irrelevant. This just shows how that we can't recover the temperature exactly using this approach with finite sampling density because of numerical errors are too big. However, if we look at the spectrum of them, they look like by getting rid of the noise in the spectrum, we can get a denoised spectrum. We can quantify the similarity between the reconstruction and synthetic data by the relative error in the spectrum, in the position of the spectrum center. Errors in wave number, Kr, and also in frequency. So they are separately defined here. So this figure shows how the relative error of wave number varies with the number of viewing chords. For each set of parameters, we run 20 times. So the randomness comes from the random phase during the generation of the fluctuations. The markers indicates the average value, and the shades represent the error bar. Note that the error of the synthetic data is due to the sampling effect. So when the errors of the reconstructed and synthetic data both being small, we can say it's a good reconstruction. So by this definition of goodness, we can find n theta equal to 6 is good enough. So the least requirement for n theta is about 6. And the same study carried out with n global, the number of global codes, and so the least requirements for n global is 9 here. And the least requirement the number of measuring points is 21. About 21. So 70 is also acceptable, actually. And for the number of local chords, it's about 29. And this is for the sampling rate. It's about 3 megahertz. So the optimal parameters are summarized here. The total number of chords we can calculate, it's about 228. And the sampling rate is 3 megahertz. Compared to the data in a recent W7X paper, they use 360 chords, and the sampling rate is 2 megahertz. So we can almost say it's feasible on this particular plasma consideration. So we also notice a problem for this algorithm is about the pollution of density fluctuations when we set the synthetic temperature fluctuation to be 0, but the density fluctuations are not 0. We still have non-trivial reconstruction. So it's artifacts. It's about one third of the case with temperature fluctuations. So it's not apparent how to remove the density fluctuations, but it's definitely important, and we'll study it later. So other things we are going to do next are, so first we are going to model the effects of signal to noise ratio. And it's associated with the beam size and the viewing chords. Without considering signal to noise ratio, the result doesn't make sense. And we are also going to change the parallel beam geometry to fan beam geometry because it's more practical. And we also consider replacing the total made up temperature and density data by the gyrokinetic simulation generated data. And also the impurities can emit subtext rays that can't be neglected, and they have many line emissions which should be avoided in our model. The existence of impurities will alert the mapping from the electron temperature and density to emissivity function, which could affect the curve fitting parts, which is it is from emissivity to temperature and not the tomography part. Thanks for your attention.